Okay, the last thing we need to look at is solving these polynomial inequalities and rational inequalities. And so on this first one, really this is the process for the polynomial ones. You find the x-intercepts and then test values between and beyond them. So the x-intercepts, what would make this equal 0 would be a 5 and a -2, right? Those are the x-intercepts. Those are what would make this equal 0. So then you ask yourself, well, is 0 greater than or equal to 0? Well, yes, it is. So I'm going to put true next to this because on my number line that I'm going to make right here, I need to put my -2 first and then put a 5 right here. Those values are going to be included. Those are part of my solution set. So I'm going to go ahead and bold those in. Now, if it would have been just a greater than symbol, then actually those points would not be included and we just put an open circle. So then what we do next is we test. We're going to test a point, and we have three subintervals right here. One of my subintervals is between -infinity and -2, -2 and 5, and 5 and infinity. So I'm going to draw these lines right here to kind of keep everything separate. So first I need to pick a point that's somewhere between -2 and -infinity. So -3 would probably be the easiest thing to pick. So then I plug in -3 for my x values. So -3 take away 5 would be -8. And then -3 plus 2 is -1. And then we ask ourselves, is that greater than or equal to 0? And so, well, when you multiply that together, +8 is greater than or equal to 0. Yeah, that's true. That's true. So since -3 works, that means all the points in the subinterval work. So that means everything between -2 and -infinity is going to work. So then now we'll test between -2 and 5. The easiest thing would be to test 0. You could test something else if you want, but 0 would be the easiest one. So 0 take away 5 would be -5. And 0 plus 2 would just be 2, right? And that's greater than or equal to 0. We're asking ourselves that. Well, this time we get -10 is greater than or equal to 0, which that is actually false. So we do not want to include that interval right here. Then last, we need to pick something between 5 and infinity. So I'm just going to go with 6. You could pick something bigger if you want, but I'm going to pick 6. So once again, I plug that in where x is at. So 6 take away 5 is 1. 6 plus 2 is 8. And then we ask ourselves, is that greater than or equal to 0? Well, 8 is greater than or equal to 0. Yeah, that would be true. So we're going to go ahead and shade from 5 to infinity. So my interval notation would be from -infinity to -2, and we'll bracket that because we get to include that. And then union from 5 to infinity. And so that's our first one. Okay, so then on the next one, looks like we have to do a little factoring to get started. So the first one was factored for us. This one, we're going to have to factor out an x squared to get started. So we'll do that. And because we're trying to find the x-intercept, so we want to know what will make this equal 0, right? So one of them is going to be 0, and the other one's going to be 6. Those are the two values that will make my left side of the inequality 0. Then we ask ourselves, is that true? When I plug that in, is 0 greater than 0? This one's actually going to be false. So what that means is that on my number line at 0 and at 6, I'm going to want to use open circle because those points are included. Now maybe the points between them or beyond them may work, and that's what we have to do next is test. So here I'm going to test, x equals -1. We'll just try -1. And so we plug it, I would plug it into the factored form. You could plug it into the original one if you want, but I'm just going to go with the factored form. So let's see, we're going to get -1 squared times -1 minus 6. Is that greater than 0? Well, let's see. Negative 1 squared, it becomes positive 1. This becomes a negative 7. 1 times negative 7 is negative 7. Is negative 7 greater than 0? No, that would be false. Negative 7 is not greater than 0, so we don't want to shade that interval here. Then we need to test a point over here, which x equals 1 would be an easy one. So let's see, we're going to have 1 squared, and then 1 minus 6, which is what? That's negative 5. And then we're asking ourselves, is that greater than 0? Well, let's see. That would become 1 times negative 5 is greater than 0. Is negative 5 greater than 0? That actually comes back false again. Okay? So a lot of times the pattern is true, false, or whatever. In this case, we have a false, false. And the reason that's happening is if you were to look at the graph of this, um, at 0, it's has a multiplicity of 2, and so what's happening is the graph, if you were to graph this, it bounces off, and then it's going to probably come back up and go through 6 right here, to where I bet this last interval will come back true. But here what happened was I had this part of it, and then I hit the x-axis, but it's an x-intercept, but I didn't actually cross it. I bounced off of it, and so that's why it came back false, false. And then the last one, it looks like it will come back greater than 0. So let's find out. So x equals 7. So if I plug in 7, 7 squared is 49, and then 7 take away 6 is 1. 49 times 1 is greater than 0. I can already see that that's going to be true. So we'll go ahead and shade right there. And so that interval is going to be from 6 to infinity. So this time I only had a single interval. All right, so now we need to look at the rational inequality, and it's done in a similar manner, except that we look for the x-intercept, but then we look also for the vertical asymptote, because typically there's a sign change on my output value at the vertical asymptote. Not always, but typically. So first, to find the x-intercept, what we do is we take the numerator and set that equal to 0. So we're going to have x minus 6 equals 0, and we'll add 6 to both sides. And so we get x equals 6. And then you ask yourself, would that be true? Because if I plug in 6, what happens is this will all become 0 right here. Is 0 greater than 0? False. 0 is not greater than 0, right? Now, if I would have had the equals 2 sign, then that would be a different story. Then it would actually come back true. Then the next part is to find the vertical asymptote. And to do that, you take the denominator and set that equal to 0. So we're going to take the x plus 2, set that equal to 0. And so we get x equals negative 2. Now that one will always be false. Okay, because vertical asymptotes, you cannot, you can't touch it. That would be undefined. So now we'll go ahead and put these values on our number line right here. So at negative 2, and we've got 6 over here, and they're both going to be open circles. Both can be open circles. And so now it's time to test those subintervals. And so over here, I'd probably just test x equals negative 3. So we'll plug that in. So let's see, negative 3 take away 6 would be negative 9. Then negative 3 plus 2 is negative 1. And we ask ourselves, is that greater than 0? Well, don't be fooled, because the double negatives do become a positive. And so it will be true, because 9 is greater than 0. And so then we'll go ahead and shade right here. Then we'll test something between these two. The easiest thing would probably be to let x be 0. So whenever you let x be 0, the numerator would be negative 6. The denominator would be positive 2. Is that greater than 0? Well, not this time, because a negative over a positive is negative. And so this one is going to be false. So we don't want to shade there. And then on my last one, we'll let x equal positive 7. Well, 7 take away 6 is 1. and 7 plus 2 is 9. Is that greater than 0? Yep. 1 over 9 is a positive number. Positive numbers are greater than 0, so that's going to come back as true. So we'll shade there. So my solution intervals are going to be from negative infinity to negative 2, parentheses, and then union in from 6 to positive infinity. All right, so that does it for the review. I hope that helps. And if you have any questions, just shoot me an email.